Welcome everyone to maybe another fun live stream. One of those days, some days you manage quite a lot, and other days it's like, yeah, somehow nothing really quite worked today. I basically wanted to get initially started here with this amazing, actually need to check ULX3S board, Fpga board, previous video that was sent to me here, and also supported with the open source toolchain, uses and stuff. And so I wanted to do some initial hello world and enablement stuff, and then 1 hour is gone, second hour is gone. Nothing much to show yet. Also partly this was packaging some open source stuff. So the stuff for this is here in SymbiofLow project. At least that is what I think what it stands for. Project Trellis. And so I packaged that in T2. And of course this didn't just work as per usual. Just a very quick summary before we go into some other details with HDMI. So I packaged this. That was, of course, here you see this already in the changelog here, just committed this. And so for that, yes, so this was not finding Boost. This is C++ and Boost, of course, not finding something. So finding Boost Python took also some 30 minutes to figure that out or hot fix it, and then it still didn't work. It would fail. And so next PNR for place and root and stuff. And you also need to rebuild next PNR. And because somehow I think, at least it looks to me, you need to hard code this. So this is like GCCs and targeting one kind of FPGA architecture. So you have to choose between ICE40 and ECP. What is it, even ECP5 or something, and ECP5 or generic. And of course this wouldn't build with some import database module. I thought this is some Python module, and I actually added here some Python databases and debugged around there also some 30 minutes until I realized in this code that this is just like some root prefix. Really funny stuff. Anyway, there you can see 30 minutes gone there, 30 minutes gone there. The good news is I got this to work now, except now also whole afternoon is gone with this kind of fun setup. By the way, welcome everyone, and I hope audio is fine. So the next thing is then with this amazing ThinkPad setup. When you run your own Linux distributions, and easily, because here, of course, Bluetooth. So today really wasn't my day packaging this stuff, except here now the stuff is packaged in T2. Also, this means I also need to look at the camera with this stuff standing like that. Also, when you run your own Linux distribution, then you usually waste a couple of hours with, today Bluetooth also didn't work. So today nothing worked, except I probably can be happy that my Linux still booted it all. So it turns out, then I spent 30 minutes with Bluetooth, and I really throw this out of the window sometime soon, which also is one of the rare cases where it's not Apple's fault. And then I wanted to go live with without Bluetooth keyboard garbage stuff, and then I couldn't go online. Pulse Audio also didn't want to pick out the HDMI capture card, and then I realized, hey, yesterday I updated UDEV, so of course the UDEV update didn't work, because so probably this UDEV garbage stuff maybe just didn't work because of UDEV update. But 2020. And if you were wondering why I'm thinking about writing my microkernel, it's really so many cooks, and at the end all the UDEV Pulse Audio. So whatever, probably later I check with the Bluetooth stuff. But in my opinion, also T2 is rocking a totally decade-old UDEV version, because the new UDEV versions come bundled with systemd, and you can imagine how much of a systemd I am. So So that is the intro of how you can waste an afternoon with packaging stuff. So to give you some summary and that you learn something at home, because that is after all here our educational funds channel. So this project trailers is the database. So what they do is, I think they also automated this. So because reverse engineering this ESP5 stuff here, the icebreaker IS40 is another, I think, was it Silicon Blue or something? Maybe latest purchase this. I didn't really Google the history of those projects, but this project Trellis here is what the icebreaker, was it icebreaker? Project Ice, whatever, you get the idea. Ice Storm, Project Ice Storm. This is reverse engineering all the bits and pieces, similar to Novo of graphic card fame, of those people sitting there all day and weekend and poking around in the bitstream. This sounds to me that this is highly automated. So what they've done, probably, it sounds to me, at least here from the summary, is using the commercial toolchain, generating some simple bitstream with just some AND or NOR, and then increasingly complex stuff, and then automatically diffing the bitstream and figuring out which bits toggle and flip and change, and running this through a massive program of automatically deriving which bits belong to what. And this is, so the good thing is we do not need to tinker ourselves with this usually pretty annoying and Windows and stuff tool chains, and we can stand on those shoulders here of this amazing giant work, and we can use the same tool chain. So for this board, just that instead of 5,000 we have 85,000 or 84,000 and 32 megabyte of SD-RAM. And one thing that is somewhat a surprise to me is that although this board is so much more advanced in terms of so many more logic cells. However, one thing is, so it has, what is a really funny thing is, it has here something that looks like HDMI. However, it isn't. So when you read this here carefully, I was already wondering why they list here GPDI, General Purpose Differential Interface. And I was wondering, like, is this HDMI or not? So, whatever. And turns out this is HDMI. However, they just don't call it HDMI, mostly because it's not like 100% compatible, and to avoid any licensing payments. So one lesson learned and one pro tip for you playing along at home: if you don't want to pay some licensing fees, then just name it like it. So here's video, GPDI connector, 3.3 5-volt I to C bidirectional level shifter, and I think somewhere they call it here GPDI. Electrically LVDS, mostly TMDS tolerant female receptacle, more or less compatible with digital monitors and DVI. So you're not even calling it here HDMI. So I think this PMOD stuff could be compatible. So very theoretically, we could probably plug in the icebreaker or any other HDMI PMOD here from previous PMODs. However, that would use those pins. So probably we best make use of this General Purpose Differential Interface, formerly known as HDMI. And so what is really fun with this is that this allows us to learn a good deal here. By the way, are quite some examples. And this means this pins, this general purpose differential interface pins, are directly connected to the Fpga. So this means we need to implement DVI TMDS ourselves, and or certainly not ourselves, but reuse this here, this code here. So in previous video, let's take a quick look here. Here are some slides that they use for their presentation and stuff. And if we take a look here, a video, or not this video, so this is exactly from their presentation what we already had in the previous videos of front porch, video visible area, back porch and sync. And we have seen in previous videos already that you can just draw differently, just draw the visible area first, then horizontal back porch, sync front porch, and just have this looking differently. But yeah, you see different people favor something else. So we still have the same video signal, and again this digital stuff is just VGA over digital. And so here's HDMI. So what we need to do is some TMDS transmitter, and I show you this only for you to learn how does it work. So this is on the icebreaker. This also is done like this. Just in the icebreaker we have the lattice silicon imaging SEL chip there on the PMOD transmitting this for us. So on the icebreaker we output, as seen on the previous videos. This video is only the short summary. Where is it even now? So many others was a pre-slide. So on the icebreaker we output also this. However, we output this with the pixel clock, the 26 megahertz, on to the bus, to the PMOD, to the external ZIL, looks like maybe no lattice, transmitter. So this means we need to encode this ourselves to this serial low voltage differential signal. And for this it is probably a good idea to take a look. Here are some papers from, for example, other FPGA project and other manufacturers. So this TMDS 225 megahertz maximum signal. So internally you may or may not know, so you can transmit there some 6, 8 something bits, and for encoding reasons, for different keeping, here's by the way somewhere it should be mentioned here. So this is dual link, by the way. So if your bandwidth is too high, single link versus dual link, I just want to go here to the signals. That should be here somewhere. So here's the serial data, and to minimize the transitions, to keep the frequency lower of the serial link, they have here some transition minimization. So they serialize this 8-bit to 9-bit, and if there are too many transitions, here's an example. For example, this is of course the maximum number of transitions, meaning each bit would flip from 0 to 1, and as you can see we would have for 8 bits 0 transmissions, so they write here too many data transitions. So they just, I think they XOR it with 1 or 101 or something, and the 9th bit is added, so you have 8 data bits and the 9th bit here is added to indicate whether it is a minimized encoding. So it could be, so what you're doing is in the transcoder you count how many transitions you have there, and if there are too many you just, I think, XOR it with 1 or 101 or something, flipping each second bit or something of that sort. We probably see this here in a second. So, and then it is also additionally, let's take a look here, by the way. Do they, by the way, write exactly for what reason? If this is just frequency or single clock channel 10-bit, yeah, we learned this already. Anyway, so additionally it is also for this transmission reasons trying to keep this DC bias as minimal as possible here with DC balancing, and this is adding a 10th bit. And they write here, one of the problems transmitting a series of ones and zeros over a cable is very high speed is the electrical characteristic of charging a line, and so this occurs when you send very long streams of ones and zeros. So at one step this kind of transmission avoids high frequencies in terms of many transitions, and on the other hand it also avoids to have very long series of ones and zeros for, or mostly ones for that time, maybe for charging this as a line acting as a large capacitor, if you want a large battery in oversimplification, but certainly it's not really a battery, it's like a capacitor. So for this it is also additionally adding a 10th bit of weather to DC balances. So what this is doing is I think completely reverting this, I think. Let's see, so this 10th bit is then indicating whether the data word required minimized transition, what? We had this 10th bit is DC balancing, and the differential signaling besides minimizing the transition helps to increase high speeds. Critical factor is increase the immunity of radio frequency and other electrical noise. So yeah, they do not really know. I always don't like this PowerPoint slides where, yeah, polarity reversed. I think this inverts the whole data word. So this is of course an oversimplification. If here would only be 1, 0, I think this would still be here. Anyway, we will see this the next days when we take a look at this. And maybe they also have here, so additionally this is a differential signal, as you see here, meaning positive and negative, and the difference of the signal, meaning if you have a noise here similar to also simple balanced audio of XLR kind of studio fame, where you have noise leaving this noise on both wires on ground, or yeah, this is like 2 wires. It's not ground. It's you have two signaling wires, and by taking the difference of the signal, you have the same noise, usually more or less on both wires of your signal, and so this differencing the signal basically removes most of this noise again from the line. And so yes, this is a pinout from DVI. I thought, let's see, do they not have some eye diagram, or was this not included in this? Anyway, this looks relatively complicated, but in reality this is relatively simple. I just wonder that here's not, I wanted another diagram also, but probably this was maybe this one. So how this looks on the signaling line is that you have, if you, this eye pattern test, what you usually do with this kind of high frequency signals, not only for video but also memory and CPUs and PCIe. So this is, as far as I remember, and in my experience, also relevant to similar high-speed signals from PCIe, where you have exactly this kind of patterns and this kind of link training. And so here's a poor signal. So this eye pattern is the digital signal on an oscilloscope of also previous videos, what we also in similar form have done here sometimes. This traces many ones and zeros overlapped together on the oscilloscope. And so this is not one, but like 10, 100 signals clocked on top of each other, so that you see here this kind of eye pattern. And the better you see here this eye, the clearer it is with the least surrounding noise here. This is a good signal and this is a poor signal. And just as an example here from just one, also some real world screenshots here, good picture, no picture, and approaching. With digital cliffs, I mean here in this cable, of course this is some cable promotion paper. Here's also how this is built up in the cable with all the TMDS links here, again with the source and destination here, just as we seen here on this previous paper presentation, and how this is on your Fpga or laptop source to your display. And again, here's this links, and this also is the reason, of course, why the digital signal, they say this here also somewhere in this article, cable length, so over, unlike analog audio or video, where the longer the cable is, the poorer or the more ghosting and less contrast your picture becomes or your audio. This is of course the same case with digital, just like with this eye pattern. The longer the cable becomes, the decoder can still decode it until the quality of the signal becomes so degraded that there is then this cliff, and then from one moment to the other you just add one more meter and the signal becomes so poor that it's this digital, either it works or it doesn't, and there is nothing in between really. And this is exactly what this eye pattern is. You have 2 meter cable, the signal is good. You have 10 meter cable and the signal might look like that. Let's see, so this is just some rough overview I wanted to give you here, taking a first look on those examples and starting to port our RISC-V icebreaker code here, and have also full VGA running, or a super, with this kind of memory we soon probably have super VGA running. Let's see, already quite some people in the audience. And Mr. Bongs asked frame grabber, so yeah, so this also means you can so because this board has, as you see, this lattice ESP5 differential pairs, not only routed to this GPIO, but also to this general purpose differential interface, aka formerly sometimes called HDMI. And this also means that you can certainly implement, I think, the reverse, right? So if you wanted to, I would expect that this should be possible to make a frame grabber out of this, just that you need some, USB is connected here. So yeah, this would be USB 2, I guess, not sure if you can, no, probably it's not enough. So this is USB 2 only, unless you make your own PMOD and stuff. But yeah, also previous videos we are using this Epiphan binary only garbage thing, and this is also running on an Fpga. So previous video, also someone, so 2 videos or 3 videos already there, Epiphan. Also another video we need to still reverse engineer this Epiphan thing. And let's see what else. Navarro didn't want to bother with TMDS, was too much of an hassle, not complicated but just a lot of work. Use the transmitter receiver. Yeah, so the good thing is this people here standing on the shoulders of giants have done this already. So this fake differential, I'm not really sure what they mean with fake differential. Maybe they mean 0. So this is not like, not sure if this should be plus minus in the TMDS DVI spec, or if this is just ground plus 3 volt or something. They write here also this G, general purpose differential signaling, is not fully HDMI compatible, but good enough to be accepted by most HDMI devices. Maybe also not really sure if this signal should otherwise be a differential. Should take a look another day. However, so they have done here this code already, so it is just this stuff, as you've seen just today, 2 or 3 or so hours spent on this already, and not even have my first Hello World running. Of course, my own fault of running an own distribution and packaging this project trailers already first and stuff. But otherwise, this code is here. So fake differential module here, relatively simple, not doing much actually. So mostly just defining those clock and TMDS clock red green for this transmitter, and outputting here the signal. You see, as in my other examples, if you understood this, and sometimes it's just very simple when you understood, and well, the complexity, the devil is in the detail. I also spent already, for example, a whole afternoon purely on getting a PLL working, which was, yeah, you define a PLL in IS-40 with Yosys, and then it doesn't synthesize because you can't connect the PLL input to another pin and drive the PLL and other logic. I don't know why, certainly some good technical reasons. But yeah, even had to private message Claire there from Joseph's fame and say, hey, can you give me a tip? What's wrong with my PLL stuff here? So yeah, then you have also HDMI video. This you see again just some definitions of instantiating here, clock generator, clock instance, VGA instance, and differential fake transmitter instance. And then you also see here this TMDS encoder. This is doing what, also by the way, apparently already free Libre code already 20 years maybe in the open. Amazing stuff. And so this is doing this XORing here. So as you see, works the differential encoding for this byte here, and count how many ones are set in the data, and then decide whether to XOR it here as we just seen in the standard, and then do the DC bias output in terms of, you see here, control period. And so this is DC bias. Need to check here what exactly this is doing. So either if the bias is that, then no disparity encoded. Yeah, would need to, but okay, so this DC bias is here, the should be 1 bit, shouldn't it? Anyway, even this, just some XORing, and there you see mostly what this commercial integrated circuits are doing is this, XORing the stuff, and so not that complex actually. What you're paying there, some dollars for this encoder, and then this VGA video looked similar. If you've seen my previous videos where we did this ourselves, we first based on one example that was a little bit off by 1 and huge, then on Mika Elizabeth Scott's example of Lime fame, and that was working mostly, except that it was outputting a signal more than the active area that confused our pixel counting, and the pixel counting was off by some blanking period. So I later rewrote this to be counting in a more usable positive integer range, the visible scan out frame buffer area. And you see here again, this is just similar to how we have done it. Horizontal visible front sync back total, and just similar you see here, if the position approaches the total, set to 0, and so on, and otherwise. Okay, it's actually doing it. So in our example, it's also an interesting way. So this is actually, the interesting thing is always to find out what is using the least logic cells. My example, so this is using in comparison, not really sure. So later, what I did later was I was counting and comparing. So it would be interesting to know, because this is using 2 comparators for each sync signal here, and also interesting. So yes, you see there's not only one way to implement it, there's, like, in the meantime, 2 examples of others, my rewrite, and this is also again a little bit different, but again similar. So code similar to our code, outputting here this VGA signal that you have seen here, and we can also show you this again. So this VGA signal of front porch, visible area, back porch sync, and then in this Verilog module composition, combining all of this here, signal generation, and so on. So next is actually, now that I have some of the basics running, actually trying it, and then see how far we are getting. The only other thing is, so I now in T2 and on my system, I packaged this project Trellis and changed next PNR. Yeah, unfortunately, you then need to configure next PNR whether you want to have support for ICE40 or ESP3. And this is a hard-coded thing then. I slightly wonder, I wish this could be slightly different. The only complication is that these examples use another like cargo kind build system that I need to take a look in. Next to this is using APIO. And so yeah, if I would want to use those examples, then I would also need to package APIO or need to see this looks like some cargo kind of thing for Fpga. And yeah, Fpga there, in case you were wondering and that you hear something else, maybe leave me in the comments below if you use this already. So either I need to package this, looks a little bit like the cargo of Fpga ecosystem stuff, but there you see of, yeah, one afternoon just getting all the toolchain Hello World stuff up, and even then I'm not done. But that is the Fpga overview. We have quite some comments also, and zero drop frames, amazing stuff. As usual, you can leave in the comments below what you learned or would like to see the most. The big summary is, of course, that this board with 84,000 logic cells allows us to build much larger stuff. And also, if there is, of course, not only is there a Pico RISC-V example that you can just get started with, there's also yeah, CPU like Pong and Pac-Man and audio stuff. And CPU-wise, wait, this is a small CPU. CPU-wise, they of course use the same Pico RISC-V like we have done. And the cool thing is, so the Pico RV32 of course supports optional compressed and even multiply and divide. And on our previous example, we couldn't really use multiply and divide, and we had to do it super slowly in software, previous video. Like simulating or emulating multiply and divide in software, like just using shifts and ors and ends and stuff. Of course, super slow, like hundreds of cycles per each divide. And with this large board, of course, we can enable hardware multiply and divide in the Pico RV32 for a speed up of 100, and approximately, your mileage may vary. And of course, here in this example, they use Pico RV32 as well, because why not? And the only thing is Pico RV32 right now does not implement an MMU. So if we want to rock Linux on this board with T2 or so, we would normally need an MMU, memory management unit, to run some real Linux, not some UC Linux, which probably not really sure if they've implemented support for that for RISC-V, because of course you need to implement support specifically for this CPU. You cannot just use UC Linux for ARM or Motorola 68K. Of course you need your RISC-V Linux support patched for MMU-less operation. And there is of course also already an RISC-V, that is VEX RISC-V. And the only thing is, it looks to be implemented in HDL, not Verilog. So I'm not really sure how easy this is to combine, unfortunately. So you could theoretically use it. Not sure if the code is in here or resources. Not really. So much to browsing this here live on YouTube. But leave in the comments below if you used any of those already. This supports in MMU, so this VEX RISC-V can run, oh we had this already, this can boot Linux. Just I'm not really sure if I want to use just this, because the integration of when we usually use Verilog, but otherwise maybe I research it, maybe it's easier than I think. So this is just like Pico RV32 implementing RISC-V 32-bit pipeline with 2 to 5 stages, depending configurable, like fetch, decode, execute, memory, write back, 1.44 MIPS per megahertz, when nearly all features are enabled, and 1.57 MIPS per megahertz when the divider lookup table is enabled, and otherwise, yeah, optimized for Fpga, optional multiply divide, just like Pico RV. Mostly interesting for us because it has an MMU, so optional hardware refilled MMU, and yeah, can boot Linux, of course. So they have here also some numbers. So it can reach on other, well, actually it has here some numbers for IS40. Actually, yeah, but this is without MMU, not really. So yeah, if you take a look here at implementations here, so with MMU, so this VEX RISC-V, you can also use an IS40 if you are not using MMU and divide in multiple. So smallest configuration, VEX RISC-V smallest, RV32i. And then of course, if you enable MMU and stuff, then yeah, other FPGAs. How many, actually it's using surprisingly 1500, yeah, but this, there you also see, let's take a look here by the way, there you see that this logic elements do not directly compare. So the same configuration here, on this example, your mileage may vary, just reading this here from this documentation, the RTX and Cyclone and IS40 LUTs here not directly comparable because, so this is listing here 494 LUTs logic lookup table things and 505 flip-flops or whatever that is. And so yeah, 494 here, 730 here. So this could also be hardware differences, what kind of details are implemented in those logic cells. And here on this IS40, 1130. So yeah, you might, numbers not easy to compare and your mileage may vary. We can also scroll here to the beginning of this slides for the end of this video, just to give you a summary. Otherwise, spending here 3 hours on a Sunday, not much achieved except debugging and packaging all the stuff. They have here a really good, in this presentation by the way, which is not my presentation here, of Milanovic and Jan Dolinay, or sorry for the pronunciation, of ULX3S presentation here. And this is a really good logic block visualization. So of probably here FPGAs like this. So you have this LUT, this lookup table, some mux, some adder, carry in, carry out, and another mux. And this implementation details vary for each FPGA vendor. So all the vendors have a little bit different stuff there, some flip-flop and some output mux. And then of course all the not only clock, but additionally some other routing input and outputs here for combining this with all the other cells for the routing logic here to route this 5000 or up to 85 or even more logic cells. Let's see, this is probably this for this video to give you a summary of what we take a look here and spend our time with. And yeah, you just wanted to do this on a Sunday and then you only managed other stuff. So I hope you enjoyed this overview, Sunday overview here. Let's take a look on the other comments. So yeah, welcome everyone. And Mr. Bonk working on some GFSUG something, 64 screen background layers and something sprites, amazing stuff. Also eliminating DC bias does away with expensive high power transmitters. Okay, interesting. There's also a Wikipedia page with 810B, looks much simpler compared to the PDF document. That is good to know. We certainly can take a look at that. Wiki 10 encoding. Yeah, so let's see, does this give you something of some value? So some 5.6, some 3.4, what is it even? Looks much simpler. Okay, I was hoping for something simpler. But anyway, fiber channel, okay, whatever. I was hoping for something else. Anyway, thanks anyway for that. Shout out. So theoretically supports USB 3 with 5G SerDes, but it's still ongoing research. Yeah, thanks for that. So this, of course, another summary also, yeah. There is an ECP, what exactly is the name of this? Yeah, ESP32. So I mentioned in the previous video what was not instantly clear to me, but I should have actually seen this always when you are in a rush. So this there is also, maybe could run this in autofocus for you to better see this at home. So this is some ESP32 of Internet of Things fame. 32 probably, judging from the name. So this is a HUL. What was instantly clear to me is that this is a wireless module, obviously Bluetooth and Wi-Fi. However, this also includes a full 32-bit microprocessor and allows this Wi-Fi, what I mentioned in the previous video. You can Wi-Fi flash this, and yeah, making the whole thing certainly very full-featured, and certainly what we try next as soon as we synthesized our Hello World stuff. But yeah, of course, like Navarro mentions, you certainly what I guess they mean is that you can implement your own USB 3 on these pins here. So if you want to sacrifice this and implement this yourself, like USB 3 logic there, then you need quite some data lines. Use here quite some GPIO pins for your USB setup. Otherwise, the second USB port is wired to the Fpga. So yeah, USB keyboard and mouse probably for us eventually in a month or two or something of that sort. And let's see. Okay, Mr. Bong still recommends some capture thing. Zero drop frames is also amazing. And yeah, as I mentioned in the previous video, there is an Amiga implementation. So there are other people who have done a whole Amiga in Fpga. So you probably can just load Pac-Man and stuff. And one thing I probably should have called out. So well, certainly super. I wish I could like spend a whole day working on this stuff, on this super thrilling, interesting stuff. This buttons here obviously arranged already that you have here directly an arrow cluster and button cluster. So as far as I've seen, you can here, even on other examples, directly play your games, vintage retro console, Pac-Man, Pong and stuff. So certainly super amazing board. Can totally recommend this. Makes super sense to me, everything that I've seen so far, including for other people. Well, I don't need this. For me, it makes it even somewhat more complicated, but I can understand the appeal of this Wi-Fi flashing. If you run this, it should have an access point. So either it tries to connect to some Wi-Fi, or if it doesn't, like you can configure this, like test. The default is whatever the default was. If it doesn't connect to the default access point, it opens its own here on this ESP32. And for me, I prefer to just plug in the cable and flash. For me, it's always like, yeah, one Wi-Fi step, but I certainly understand that many people find it easy to do it wirelessly. And yeah, for running our own stuff, I hope, and not yet checked, I hope we can also get access to the Wi-Fi and Bluetooth from the Fpga. So if we have our whole RISC-V Linux or something homebrew system here, that we can have Wi-Fi and Bluetooth here with the system. And I said this before with this ICE40 icebreaker. This kind of systems I find much more thrilling and useful than the 8-bit guy's vintage retro system with a hardwired, I think probably 6502 or something of that sort, because this is so much more flexible with this kind of board. While I certainly appreciate the effort that the 8-bit guy and the team is putting in there, also they're not focused because yeah, autofocus is so 80s, I guess. While I sorry for it's just on a small tripod here. this kind of system is such more versatile, so from that point of view I can totally recommend this. Either whether you want to do some vintage retro stuff, some Sega Master System, some Super NES, some maybe even what was the name of this 3D something, Nintendo 30, whatever, I don't know, whatever, or Amiga and Commodore certainly, but Amiga and stuff, super powerful. Or for our case, so we can have one open hardware board and one like crowd-funded campaign, and whether you want to use this for Linux development, professional stuff or homebrew stuff, this serves so many purposes, and from this point of view I would much rather recommend this kind of board setup, even with included general purpose differential interface to connect it to some displays, and don't call it HDMI. That's it for this video. I hope you learned something, and of course we have quite some comments. Not really sure if it's always the best idea to read all the comments, but so Navarro theoretically supports, okay, we had this. Video grabber, specifically Vision something Cyclone. Well, the Epiphan also uses some, what was it, Spartan something. Let's quickly, or what was this, Fpga something. Yeah, some Spartan 7, I think it was. And yeah, so I have already this frame grabber, it's pretty good. I probably need to just do a proper driver. Yeah, Mr. Bonk, I read that the FSF, Free Software Foundation, sent a hard drive to Windows for Windows source code, to Microsoft didn't. Well, it's a bit pointless thing, but yeah, whatever. Navarro doesn't really want to look at this code. By the way, did you know at some point of time some Windows NT 4 source code leaked at one point in time? If you're into this kind of thing. But they of course will not release the source code anyway, in my opinion. So yeah, UC Linux, so Mr. Bonk, UC Linux something. Someone made a, Mr. Bonk knows someone made a pipeline version of 6502. This pipeline version run 2 to 3 times faster than this NMOS 6502 here, probably. And Christian says this explains why I mention regression all the time. I don't like Windows either, but making stuff to favorite choice is just stupid. Yeah, so this is, how many people do we still have watching? So this is, again, if you're watching the whole video, sometimes the issue is not only was I busy the last days, but when I spent the better part of a Sunday and have not much to show, then at least some general overview. And also, yeah, regressions. Of course, I could just run Fedora and stuff, but then you would not have this cross-compile environment of T2, of compiling to RISC-V and stuff. What annoys me the most with Linux is so many there in German there is some saying like many cooks, so like the direct translation, probably you have it in your language, leave me in the comments below if you have or not. Like many cooks like ruin the meal, and that's a little bit, probably I thought today is quite well fit into the open source situation. There are so many people and like to reinvent the wheel and need to change something just to change something, and then like each time I update UDEF, some stuff is broken, and yeah, then also I started X with then if your UDEF is broken, then even your X doesn't work because it's usually configured for auto detection, and if the input devices are not marked with UDEF input whatever, then your amazing auto configuration Xorg server is not picking up any input devices, and you have a dead, like you run start X or something and your machine is basically dead because you have no input anymore. And this, yeah. And yeah, after 20 years, of course, I will continue to run my T2 Linux, but my impression is this would be so much more amazing with a really nicely designed microkernel system without all those. In Linux, it's like we have this kernel, which, yeah, one address space, everything can memory clobber off by one itself all over the place. And then we have all the user space, nothing designed, everything written in C, everything clobbered together and for decades changed until it was working a little bit. And yeah, to be honest, after 2 decades, it becomes a little bit tiresome. And I also feel that we in the open source community somewhat missed to modernize it with like modern languages. In my opinion, it's with all the security vulnerabilities and stuff. It's, I have to say, not up to the day that we have all the Linux infrastructure in C from, well, the C library, but even the Linux kernel, to dbus, udev, systemd, Xorg server. It's like, yeah, if this would be a commercial company, everyone would be laughing about, just like they are over Microsoft. But yeah, this is a story for another video. But just like, yeah. What else do we have here? So Windows stuff, Wi-Fi to what? Yeah, Christian likes the idea of ESP32. And he agrees that is Tinker Heaven. Yeah, I need to check how the Wi-Fi is directly connected if you have only 11 115K baud Wi-Fi. That would be set, but better than nothing. But yeah, certainly if you want high speed, also by the way, as they have here written for Ethernet could probably be done here on this general purpose differential thing, because HDMI has optional pins for audio and Ethernet. So maybe you could, or the easiest certainly is to make some special dongle cable here of HDMI stuff and wire, so implement Ethernet here on this general purpose differential pins and have some external Ethernet physical on a GP, general purpose differential interface, HDMI breakout cable stuff, and then you have a already pretty neat system. And yeah, not really sure, leave in the comments below. Mr. Bonk writes, I start installing Temple OS, and no, I start to install my own OS, which certainly will be much more amazing than Temple OS. And so Commander X11 uses 6502 running on 8 megahertz. Yeah. And yeah, leave in the comments below what you think, X16 versus RX32. That's it for this video. Also, you can leave in the comments below, not really sure what is the best thing to deal with the comments. When we read them and discuss them, then usually the videos are twice as long. Maybe it would actually make sense if I stop the live stream and start a new one. Then we have the commentary, the discussion, then we have like the primary content live, and then a separate video of comment discussion. Maybe that is more helpful for people watching this later. Maybe not. Leave me in the comments below what you think. That's it for this video. Also, 0 drop frames here on not our office cable because Vodafone cable can't deliver reliable business cable in 2020. So anyway, unlike the office DOCSIS cable, give it a thumbs up if you like this overview. I hope you learned something and find this as thrilling and entertaining and amazing as I do. And I hope to see you soon for our next videos and live streams to come.